Hi, good morning, everyone. Thanks for joining. Small group in the room. Hopefully, we have a good group online. It's my real pleasure to welcome Jason Hassenstab here to what I think is our final lecture before our summer break. So Dr. Hassenstab is the Norman J. Professor of Neurology and of Psychological and Brain Sciences at Washington University in St. Louis, where he's also the director of the Cognition Core for the Dominantly Inherited Alzheimer's Network and the Diane TU program, as well as a principal investigator on a number of independent research projects. Jason's really been a pioneer in the field of self-administered smartphone-based cognitive assessments using ultra-brief burst paradigms. I've followed Jason's work for a long time as we've contemplated for my own research program, which is also really interested in novel assessments. And as we've sort of tried to push the field of neuropsychology to think beyond the 3-hour battery in the windowless room with the white noise machine outside the door into real world settings that are hopefully more ecologically valid, but also certainly more accessible. So welcome, Jason, to tell us what we can learn from digital cognitive assessments. Thanks, Jason.
Thanks. I hope there's a whole crew of people online. And because there's a huge group in the room here, at least five people. But thanks. It's a real pleasure to come back to San Diego. I love visiting here. I come here a couple times a year for conferences or meetings, and I always love visiting. However, I tried to move here 2 times in my career. The first was for graduate school, denied. The second one, which I just disclosed to Mark Bondi last night at dinner, was I applied for internship here during my final years of my clinical psychology program, and I was also not accepted. So,
Wasn't my fault.
It's kind of but no hard feelings. I ended up doing just fine. Obviously, I'm okay. But I do have a fondness in my heart for this area, and it was solidified last night and yesterday with all the meetings I had. So thanks so much for having me. So let's get into this. I have some disclosures I'm supposed to put on here. None of these are really relevant for the talk I'm giving today, but my university requires that I show you them. So let's move on to the overview. So I'm going to try and cover way too much in the hour that I have, or the less than hour that I have. So I hope I get to the last couple things because they're brand new data that I've never shown anyone, and I'm kind of nervous to show it to anybody. But I want to just really quickly go over digital approaches for cognition, and we'll talk a little bit about how we do assessments with smartphones. Also some new data here on learning and forgetting rates. And then I'll talk a lot about variability and some new data with mood and fatigue, some assessment context when you do remote assessments. People always ask about this. What was the room like? Was it really distracting? And does that matter? And then the last thing is the new data that we've just submitted like a week ago from my PhD student, Samita, about how technology familiarity and age differences impact remote data collection. And the effects are really interesting. So to get into it, I always like to remind people this was probably the first digital cognitive measure, 1972, the electronic stopwatch. But what can we learn from digital cognition? There's a lot of ways to assess it. I think the thing where we started was probably like the version of a digital clipboard, an automatic entry system. So instead of sitting there with a clipboard and writing it, it was like a tablet. I mean, it was automatically captured. That's called an ECOA, or electronic clinical outcome assessment measure. Then there's digital versions of paper tests. So one of the first ones I ever saw was a tablet where someone was doing the trail making test, or the Ray complex figure, or the digital clock. You could use the device to actually transcribe and then play back how their process was for collecting that data. Then there's tests that were designed for digital administration, and I'm just listing a few here. The first 2 that were kind of big in the early 2000s were CogState and CanTab. Then there's newer approaches like Neotive, there's NeuroUX, which Rayanne Moore here at San Diego does. There's C-Hero Quest, there's dozens and dozens of others. And then I think there was a lot of platforms that were designed for or came out of specific studies. Like there's the All FTD app, which I think has now just been changed names. There's my app, which is called Ambulatory Research and Cognition. There's the branch mobile app from Harvard. There's mobile monitoring cognitive change from Penn State and many, many others. So there's a lot of different designs, but there's also different ways to collect data. And should you do it remotely or in person? It's digital, but if you do it in person, it has advantages and disadvantages. And if you do it remotely, it has advantages and disadvantages. So in clinic, you can control the environment. You usually get a consistent device type. Everyone is using the device that I give them. You get instant data capture, you get less technical issues, but the disadvantages are it's kind of a weird place to take tests. You're like stressed out. You might be getting a diagnosis of Alzheimer's today or something else, and you meet this new person and they sit across from you and they test you, and it's a little stressful. And then the other thing is you just assess cognition once because it's not very efficient to keep bringing people back in over and over. But if you do it remote, first of all, you have to think about a supervised remote, which is sort of like teleneuropsychology. And then, or is it like fully remote where the person is not supervised? Well, you can reach a lot more people this way, hypothetically. You sort of get a better sampling of general public. The environment is much more familiar for people, so there's usually removing some of that noise. But adherence is really, really one of the biggest challenges we have in remote studies. Getting people to do cognitive tests, as much as we as neuropsychologists think they are really great and fun, it turns out people really don't like to take them, especially memory tests. They don't like getting their memory tested. We've figured that out the hard way. There's tech support needs for people too. It's really difficult. Even though people are aging into technology, and I'll talk about this at the end, there's still a lot of barriers there. And if you do supervised remote, you really have to control a lot of things like, does our camera work? Can they say you? Does the internet go in and out? Do they understand how to use Zoom? You guys understand. I like to talk about high frequency cognitive assessments. And I'm going to get just a little bit philosophical here. I view cognition as a non-stationary process. I think the variation we see in cognition is normal. It goes up and down. I woke up really, really early yesterday and got on a plane and flew to San Diego. And when I landed, I probably was not at my best, but after a coffee and a few intellectually stimulating conversations, maybe I was a little bit better. So it goes up and down, and that's normal. And you can never avoid that. And it's not measurement error. That's the other thing. You can't just make a better and better test and think you're going to get over that. But I also think that those performance dynamics are meaningful and can actually signal risk for longer term changes. So we should embrace that up and downness. Like it's a good thing. Context linked changes and variation, as I said before, people are sick. They're sad when they come to the clinic. And the next time they might be better. There's how aroused they are that day. They're tired from traveling to the site. All these things impact cognition, and you'll never get rid of those influences. So high frequency assessments, we think of them as distributed, typically brief assessments that are administered digitally. And the key thing is that they're in participants' everyday lives. We refer to this as measurement burst designs. And if you come away with nothing else today, you should be convinced that burst data is extraordinarily reliable, like upper 0.9s of reliability, closer to like what you would get with like a PET scan or an MRI scan. They have really unique attributes. So you can do things that you just can't do with normal assessments. You can look at learning rates. This is a really cool area, which I'm fascinated with. I've been fascinated with for like 10 years. You can look at long-term forgetting rates because you're not limited to like that one-time assessment paradigm. You can monitor variability across different time epochs. We've looked at it at the weekly. We've looked at it at the hourly. We've looked at it at the moment to moment, which I'll show you data from. And then you can look at really cool things like how well did they sleep the night before? How much are they exercising? All sorts of different things you can do with this approach. I want to tell you a little bit about learning. And this is a paradigm that I've been working on with Yen-Ying Lim from Monash University for almost 10 years now, called the online repeatable cognitive assessment. And statistical learning is just the type of learning that happens when two things frequently occur together over time. I mistakenly called this implicit learning, and a reviewer absolutely skewered me, who was definitely a hardcore cognitive psychologist, and this is not implicit. So I'm very carefully saying statistical learning. In this paradigm, we basically teach people to recognize Chinese characters by just matching it against the English word and the Chinese word are shown together, and we tell them nothing whether they're getting it right or wrong. In the original paradigm, we had them learn 50 Chinese characters each day, It took about 20 or 30, even 35 minutes per day for 5 to 6 days. That's a lot of testing. It's way too much. And I'll explain how this works just so you understand. But the key thing here is over repeated exposures to correct pairings, participants start to make these associations. I would say implicit associations, but they're statistical associations. After 5 to 6 days, you would see the correct pairing 12 to 15 times more often than you would see an incorrect pairing. And if you think about it, this is kind of how we all learn language. No one sat there with flashcards and said like ball, and here's the word for ball. You just sort of picked it up because you heard people pair those things together naturally. And so this is what it actually looks like. So you might see a Chinese character, then you might see the English word written with it, and you would say, oh, that's not the right one. And then later you would see the same Chinese character again with a different word, but over time you saw the correct pairing much more often. And this is how this actually worked. And what we saw was a huge age effect and a massive effect of amyloid in totally cognitively normal people. So older adults took much longer to learn the correct pairings, and amyloid positive participants were much slower to learn the pairings, despite performing totally normally on other cognitive tests. No differences between groups on standard measures, but when we pushed them to learn this language paradigm, we saw massive effects. These Cohen's D's are approaching 2. For a separation between amyloid positive and negative, I don't think I've ever seen a larger effect than this. I thought this was remarkable. But the problem with this test were a lot. People hated it. The first day, you're not told whether you were right or wrong. You're just guessing at these correct answers, and they're just like, I give up. So we had a huge attrition problem, probably about 25%. It took about 3 hours over, 5 or 6 days, depending on the different paradigms that we tried. So we said, what if we can put this into our high frequency platform? We're going to go down from 50 characters. We're just going to take it down to 8 Chinese characters. And we're going to study this over just 2 days, 6 sessions at a time for 2 minutes each. And I'll show you what this actually looks like. So the total assessment time was about 12 minutes per day, up to 24 minutes total. So taking it from 3+ hours down to 24 minutes. This did achieve a lot. The day 1 dropout and attrition were massively reduced, only like 10%. So we cut it in half. Here's what it actually looks like. This is a PowerPoint version of the app. I couldn't find screenshots, so apologize. It looks a lot better than this. But you would see the word, a character, and then they're just asked to match. They're just told, hit a button. Is this correct match or not? And again, no feedback is given. That's critical with this task. Then they would see it again with it, maybe a different character. And I think this is the word for father. I'm not sure if anyone reads Chinese characters, but I think that's father. And they would say yes or no. I've kind of learned them just from looking at the task myself. And then again, you might see a different character and a different character with a different word. You can see how this works. And so this just goes over and over, cycles through them, and they just guess, yes, yes, no. And by like the second or third time through, I can tell you as someone who's done this many times, you start to see a pattern. Okay, I think this one goes with this because I've just seen this so often and it just seems right. It's kind of a weird phenomenon. And sure enough, we were able to find very significant learning curves in people. And what we did in this paradigm, you can see this is version 6 up there. So we've tested this, I think we ended up doing at least 20 different versions now. And we would do like 30, 40 people at a time using online samples. So we'd have dropout. But everybody learns, but we wanted to see if there was some sort of practice effect. And so we started a new set of 8 characters on day 2 for half of this sample. And sure enough, at first, everyone just responds at chance levels. They're just taking a 50-50 guess. But over time and over repetitions, they start to learn it, and they eventually get up to like 80% correct. So this is the same data, just presented in a different way, just the numeric version of the same data you just saw. So you can see on day 1, cruising along when they first start, they're just basically guessing 50% correct. And by the end of the day, they're about 70% correct. By the end of the second day, most people are about 85% correct. And when we started a new set of characters over, they went right back to like random guessing and then basically worked up right where they ended up. So this is a cool way to use smartphone data, I think, to spread out a learning task that you can't do with typical assessments. And the high frequency paradigm shortened the task from 3 hours down to like 24 minutes. I'm pretty proud of this. So we're now doing this in our older adults in the Diane study. And we've only got a few dozen people through this far, so I don't have any data to show you on this. But I've talked about learning. But what about forgetting, kind of the opposite side of the memory paradigm? So in long-term forgetting, which is not a new idea, been done for a really long time, we actually extend that typical delayed recall out from, the typical 20, 30 minutes that we do in the clinic to days, weeks, or even months. And there is something really unique about stretching this out, especially in people who are at risk for, or maybe have a genetic mutation for Alzheimer's disease like they do in Diane. What Phil Weston did and Nick Fox, who are my colleagues on this study that we're running, relative to about 14 non-carriers, so people who are cognitively normal but had no genetic risk for Alzheimer's disease, and people who are carrying a pathogenic causal mutation for Alzheimer's disease, 21 of them, the carriers had 30% lower retention of a word list after 7 days compared to non-carriers, and 20% lower story retention. So what this looks like is here you do your typical immediate recall, like 3 trials of a learning test. Then you do your 30-minute recall, and there were no differences between groups. But if you stretched out that recall to 7 days, that's where you started to see big separations, up to a 30% difference in separation after 7 days. Hi. This was a typical list learning paradigm where they were given I think in this case, it was a 12-word list. They were tested 3 times, and they had to, it was presented to them 3 times. And if they didn't meet a minimum criterion of retention of, I think it was like 90%, they kept giving it to them until they got 90%. In the study I'm doing now, we did not teach to a criterion. We just did a standard three trial administration. And I'll show you some data on that. So we've recently, also, I just wanted to point out, there are no differences on standard tests. So that's what I think makes this like such a cool paradigm. So we were able to pull out something that our standard tests couldn't just by extending this recall out 7 days. Same thing with the learning paradigm. We couldn't see anything on standard tests, but if we challenged them and asked them to learn something, that's where we saw something going on. So we've done this now. We've come up with a way to do a list learning test where it's free recall, not recognition, because I think that's really, really important online, by having people on their phones type out the words. And what we've done is during the recall period, because it takes a lot of working memory to type out the entire word, we picked words that had different 3-letter starts. And that way, once they typed the first three letters, the word would autocomplete. And that way we were able to get something that approached an actual list learning paradigm where people were typing in responses. And I know some of you might be thinking, why didn't you do audio recordings? Well, that's a whole side story, which I won't get into. But basically, this works. It worked just fine. And we're just now getting this started. And I'm just going to show you some data from like the first 10 or 12 people. And then we also came up with a version of a card matching game based off of the classic children's game called Memory, which I think has a different word in the UK. There's a different name for the game. I forgot what it is. But basically, you see a bunch of cards that are face down. You have to flip them over, and you sort of learn where the matches are. And then you do this 3 times. And then later, you just start with all the cards face down, and you just have to remember where the pairs were if you don't remember this game. And so the number of flips to complete 8 matching pairs is the primary outcome measure. And so after 6 days, the really long day, and we also did a 30-minute delay, which we called we called it the RLD, the really long delay, and then we had the RFLD, which I won't tell you what that is for the 30-day version, but I'm just going to show you the 6-day version here. And what we found is that the list recall produced a massive decay. So we don't have anything right now that any group level data here, but we got a huge decay after 6 days on the list learning and a pretty big decay on the card flip task. And we have another paradigm with a open-ended foils choice matching shape task that we're piloting now. Okay, I want to move on to burst assessments. What we do with our design currently, and this is in our older adults at our Alzheimer's Disease Center, is we give 3 different tests. We have an associate memory paradigm, a working memory paradigm, and a choice response time task. And we administer this in random order up to 4 times per day, 7 days consistently. So people are randomized. Sorry. the order the test is randomized and the time of day is randomized based on their availability. So for example, this participant said between 7 a.m. and 10 p.m., you can send me a notification. It has to be a minimum of 8 hours. And we use quasi-random intervals. So it's separated by at least 2 hours. That way we can make sure we capture enough data at night, enough data in the morning, enough data in the middle of the day. But of course, people don't always do them. And we put it out. And this looks like a lot of testing. I agree. It's actually only about an hour and 15 minutes of testing if you add it all up. But it's a good way to get good spacing and measure people throughout the day and look at cool things like variability, which I'll tell you about here. So this type of paradigm can give you a lot of different information when you measure people really frequently. So this is a paper we did with Zita Orovich from Penn State University, and each color represents one burst. So one of these would be going into one of each color here. And in this case, they were separated by, I think, 6 months or 12 months. And you can get all sorts of interesting information from this. So first of all, you can look, this is a response time task. So faster responses are better. So you can see when they first start out, they're pretty slow up here. And then as they get accustomed to the task, their performance speeds up. So you can look at this initial peak performance. And then after 12 months or a time epoch goes by, you can look at how much they forgot and sort of where do they sort of start the next time. That's the forgetting paradigm. Then you can look at the change in that peak performance. So this person looks like it's just like a big practice effect. But if you look at the peak performance, it would suggest they're actually getting worse over time. So their best performance on this after they sort of asymptote is actually increasing in amount of time. You can also model retest across all these bursts. You can model retest within each burst. And then, of course, as I just said, you can look at the change in peak performance. So just with a simple response time test that people don't mind doing, they actually like it. They think it's really gamey and fun. You can get all sorts of really cool outcomes that you just can't do with standard tests. So another way to look at this is with this really cool modeling technique that Zita's come up with, which is a Bayesian approach. So the thing I want to talk about the most here is variability. So how much error is there around that asymptotic performance? And so it's like this sort of paradigm. You can see in this data, these are people that have CDR greater than 0 and CDR 0. And we found some really nice effects across time just using a simple response time task. So variability as an outcome, I think, is super cool. And I always like to show this figure just to give you a little bit of scene setting. This is from my former postdoc, Andy Aschenbrenner, who's now at University of Kansas, just got his first R01, doing great, super proud of him. But these two individuals, it doesn't take a scientist to tell you that they are very different from each other, even though they have the same mean performance. If you average across them, they have the same mean. And also, I think it's important to point out that if you sampled people on any two of these points, so if you took the orange line at any point and the sort of blue line at any point, you might get a very different idea, of where they're at. But if you average across them, you get the same thing. But if you look at the standard deviation, you get something very different. You can also model variability at really different timescales. So this is simulated data that I made with ChatGPT. So, just for illustrative models. But you can look across different time epochs at how much variability is there. And then you can do this in a lot of different ways. You can make each one of those a point estimate just by averaging across those assessments at each occasion. And you can model those different trajectories. You can look much more deeply within an occasion and try to understand variability at the day level or the week level. So for example, this is what that would look like over a week. You can then get into it on Monday and compare it to how their variability was on Tuesday. Or you could look at the morning and look at the evening. There's just many different ways you can model this type of data. So time scales sort of matter. And that's what we've shown in a couple of really interesting studies. So we can model variability at the week. We can model it within the hour by hour, morning, afternoon, and then we can look at it at the session level. And so I'm going to start with the sort of daily level, like how much do people vary from hour to hour? And sure enough, Andy found in totally cognitively normal people, if you carry at least one copy of the ApoE4 allele, you have more variability in response time and spatial memory, going from hour to hour. I just think that's a remarkable thing. Just nothing else going on except carrying an E4 risk allele for Alzheimer's disease, we were able to find this effect. And it's kind of a large effect, not massive, but pretty significant. I was like pretty surprised. So then my former postdoc, Matt Wellhalf, who's now at North Carolina A&T University, he said, well, what if we did that same thing, but we zoomed in a little bit even more and just said, can we find a signal at the trial by trial level? So he said, and I said, no way. There's no way this will work. It's not going to work. There's just too much variation. There's not enough sampling. So this is like 30 seconds worth of data per person. You're not going to find an E4 signal at that level. Well, I was wrong. He was right. First of all, we found a difference between people who are symptomatic and not symptomatic, which is maybe not so surprising. But again, he drilled down and said, let's look for an E4 effect. And I said, no way. And sure enough, we found that the E4 carriers had more variability at the trial by trial level. So I think this is kind of remarkable. It's like 30 seconds worth of data. We were able to extract a meaningful signal just by looking at the way that they fluctuate around their own mean. I was kind of blown away by that. Then my PhD student, Hannah, this is a few years ago now, when she was like a first year student, said, well, you measure cognition throughout the day. And in Alzheimer's disease, we know about this thing called sundowning, where people get worse. They have more agitation. They have more variability later in the day. People have like mood problems. They report more cognitive problems than their caretakers. And so we said, well, does that exist in the preclinical state, like prior to the onset of symptoms? So we separated people, their cognitive data, into morning and evening epochs. And sure enough, we found that older adults were a little bit worse in the afternoon. Okay, not so interesting. You know, probably everybody here kind of understands what the afternoon slump is. But when we looked at their Alzheimer's disease biomarkers, we found that the people who are CSF positive did even worse in the evening hours, up to 10 or 15% worse than their biomarker negative counterparts. So it's kind of a cool way to look at time of day effects. Again, something you can't do with normal assessments. All right, I'm cruising through. This is great. So I have a really talented undergrad who is hopefully going to start her PhD with me in the next year. And she started looking into how mood and arousal affect cognition on our paradigm. So right before everybody takes our cognitive tests, we ask them to rate. This is an actual screenshot from the app. How do you feel right now? And we give them a sliding bar. And we also say, like, what's your overall mood right now? Are you in a good mood? Are you in a bad mood? It takes like 4 seconds on average, 3 seconds for people to answer these. I mean, they have to touch the bar too, so they don't just tap and get out of it. They actually have to move it. And then we wanted to see if these affected cognition, because everybody is concerned and worried about this as something, you know, as a momentary effect. Obviously, when you ask people like, how do you feel and how do you rate your mood right now, and you're asking about being sleepy and tired or active, these two survey questions were really, really highly correlated, about 0.7. So, and some people would say you're basically asking the same thing with these. But how do they affect cognition? Well, first of all, there was a really unique finding, which we keep running into with these momentary assessments, of this inverted U shape, or a U shape, depending on the outcome, where high and low levels of arousal, of sleep, of mood start to impact cognition. But interestingly, it's not just like the bad mood. It's when people are reporting being really aroused, or really, they slept really, really poorly. They actually can do better on cognition, which is like, what? So what we did is we person-centered everyone. And then we asked, we looked at the data when they were rated themselves as like the least aroused and the most aroused. So the most sleepy or tired and the most awake. And we found this inverted U shape. And so this data is reversed. So they actually, a higher score is worse on the composite. I'm sorry. So I should have flipped this around. We did it in the paper, but not on these slides. So they performed worse when they were at low levels of arousal, and also worse when they were at high levels of arousal, which I thought was really, really interesting. But we didn't see any sort of difference whether they were symptomatic or cognitively normal. And we also repeated this with ApoE4, and we didn't see anything. So we sound, there's a big intercept level effect on the performance on this, which, you know, is there, but there's no interaction at all. And these are these are generalized additive mixture models for nonlinear. So it adds a smoothing term to your model that allows you to model the nonlinear effect. So nothing going on with genetic status, nothing going on with symptomatic status, but a big consistent effect of arousal across, didn't matter whether you were symptomatic or not. Okay, another question we get a lot when you do remote testing, which I think is a very valid one, is what about where you take the test? What about who you were with? And these sort of contextual factors, are they really, really important? Do they impact how cognition operates? And the answer to that from us is not a whole lot unless you're symptomatic. So we ask people before each testing session, they complete a very quick survey about who they're with and where they are at that moment. So here's what it actually looks like. Screenshots are not as nice. And we just published this last year. So we ask, where are you right now? My home, my work, school, somewhere else, in a vehicle, outside. And we also ask who you're with, nobody, partner, family, pet. And by the way, we had many debates on whether to include pets as part of people's being with someone or not. And we decided that it didn't matter in the analyses, but it was very common for people when they were at home to select that their pet was with them. So it didn't actually matter in the data, but there was a lot of fun debates about this in the lab. And here's what we found. So if you're cognitively normal, first of all, we're just asked the question about location and social context. First of all, like, are you alone when you took the test, or were you around other people? And if you're cognitively normal, it didn't seem to matter at all. And it also didn't seem to matter if you were home or not at home. Didn't matter at all. So you could be away from home and with other people, had no impact on performance as long as you're cognitively normal. Or you could be at home and with people, didn't matter. But if you're symptomatic, which is only just 10% of the sample here, so just the one caveat, but it's still 41 people, it started to impact people a little bit more. So when people were in the most distracting environments, we found that it impacted cognition a little bit, not terribly. But if they were with someone and not at home, that seemed to be where we saw actual effects on cognition. But again, only in people who had active symptoms of Alzheimer's disease. So probably we don't use MCI very much at WashU because of John Morris, but these people are MCI. Okay, just think of it that way. Okay. Yeah. Average age in this study is 78. So these are older adults. Diane just asked if you couldn't hear online. Yeah, so these are all from our Alzheimer's Disease Research Center. And we asked the same thing on working memory. We found kind of the same thing. But interestingly, with working memory, they started to, when they were alone but not at home, they started to get a little bit better, which I thought was like really interesting. So there's stuff going on here, more work to be done, larger sample sizes, but I think this answers this sort of question in a kind of unique way. But the other thing we discovered in this study is that we asked people after each testing session, were you interrupted while you take the test? Because this happens a lot. They get a text message, they get a phone call, or they're in the middle of a test and someone says, hey, where's this? What's going on with this? And these were a lot more common than we anticipated. I was expecting something like 5% of sessions, but it ended up being about 12% of the time. And so we removed all of those sessions and repeated all these analyses, and the results still held. It still was a thing about being away from home and being with other people and only in the symptomatic participants. So overall, these effect sizes, I don't want to exaggerate them. They're pretty small. The Cohen's D's are less than 0.1. I mean, they're significant, but they're small. But the other thing we learned from, I think, this studies is that interruptions are super, super common, and you need to ask for them if you're doing remote studies. You need to ask people about them. When given an opportunity to self-identify their interruptions, the effects were a little bit reduced, not much, but I'm just saying overall, these are really, really small effects of distraction. So I don't think we need to worry about being distracted when people are taking remote tests as much as you might think. Okay, I've already sort of said all this. Super, super important to assess that interruption question. Now I'm getting to the part where I'm a little bit nervous to show this data because this is the new stuff. Okay. Does technology familiarity matter? In almost I've published like 12 or 15 papers on digital cognition now, and I've written 2 or 3 different grants. And every single time we get questions about the familiarity with technology and whether this matters. People still have a lot of biases about older adults and their ability to use cognition. We get questions about this consistently. We just did in reviews that we just got back a couple of days ago. And so I wanted to answer this question a little bit more concretely. And we've done this in one of our first papers where we actually created an objective measure of technology familiarity, where we showed people icons. We showed people like app icons and like the Bluetooth icon, and we had them identify it. And then, of course, we asked them about their technology use. And we found that older adults were far less familiar with technology than younger adults. No surprise. But that was older data. I think the pandemic has amplified older adults' use of technology and probably removed a lot of this bias, but it's still a pretty large effect. So what we wanted to do in this study was to look at whether generational differences in technology familiarity are important for digital assessments. So we call this tech natives versus tech adopters. And there's some history behind this. So 91% of Americans own a smartphone. I think that's low. I think it's of adults. I think it's probably closer to like 98 at this point. But above age 65, it's only about 79%. Now, this is data from Pew, and it's from 2024, which means they probably collected it 2 years before that. I don't know about you guys. I don't know that I buy that it's even 79% anymore. I think it's probably even higher. But there are still people that in our clinic, in our Alzheimer's disease clinic, and in our lecanemab and our medication clinics that come in that don't own smartphones because we ask them. So it's definitely more common in older adults to not be familiar. Then there's this concept of digital nativity and digital immigrants, which has been published on. And this has to do with how you grew up. Like, what era did you grow up in? Well, the evolution of technologies followed a pattern, obviously. There's a mechanical era. So if you were born in that before World War II, like my parents were born like in 1941. So they're sort of part of this mechanical, getting into the electromechanical era when they were in their childhood. And then there's a sort of software generation, which people who were in their kind of prime development years in 1980 and after, which I'm part of just barely. And the people that grew up with technology as just part of everyday life. So we use the dominantly inherited Alzheimer network, where the average age is 38 years for this study. They've likely been using smartphones for 15 plus years, ever since they first sort of came out. Most of these people, if not all of them, grew up in the software era. And then we compared them to our older adults in our Knight Alzheimer's Disease Research Center, where the average age is 77 years. So we have a 40-year age gap between these two samples. Most of these people, they're pretty highly educated, like at all our ADRCs. They've had smartphones for a few years, but definitely not all. And most of these people grew up in the mechanical or electromechanical era. We have a participant in our study who's 101 years old, and she started using a smartphone for our study at age 98, which I just love. And she's super cute. And she came in, and she had a case picked out for the phone she wanted. It was like really cute. So, and we let her pick a phone. She was 98 years old. Yes, you can use that case. It's great. Okay. We had 4 hypotheses here. The older ADRC participants, I thought, would have better adherence. Remember, we asked people to take these tests 28 times in a week. That's a lot. The Diane participants are younger. They're working. There's a lot of things going on there. But we also thought, despite having lower adherence, the Diane participants would have more reliable data. And I can tell you a little bit about that if you would like. We also thought that Diane participants would show less practice effects. And this is opposite to what we typically see in the literature. Practice effects are usually greater in younger adults and there's less practice effects observed in older adults. And I can tell you why I think that, and it has all about being facile and fluent with technology. And then I also thought the data collected from smartphones will have stronger correlations with in-clinic cognitive tests. Sorry, I should have added this in the younger adults compared to the older adults. So I thought the Diane participants would have stronger correlations with in-clinic cognitive tests. So what do we find? Well, first of all, just to tell you about the study, we have far fewer people in Diane at the time. This number is now much closer to 200. people. We had a lot of recruitment and tech challenges, and also to do a protocol amendment in Diane takes about 18 months globally. So it's been a slog. The estimated year of onset in this participant population was about minus 13 years. So just to give you an idea, that means that they're expected to have like a CDR greater than 0 or onset of symptomatic dementia about 13 years after the time at which we saw them. The age was about 37, which I already covered. The education levels are much more typical of a general population in Diane than they are in an ADRC population. And in this case, we didn't have to give a smartphone to anybody in the study. They all had their own smartphones. And about 10% of the sample had mild AD symptoms. And it was about the same in the night ADRC. But here we have 489 people. About 10% of them had symptoms, 40 years older, higher education. And we had to give just a handful of people smartphones because they either didn't own them or their smartphone that they came into the study with was like too old for us to use. Okay. Adherence. This is our first hypothesis. So as predicted, the adherence in Diane was much, much less. It was about 57%, or it was about 77 or 78% in the night ADRC. And I thought we would see like a bimodal distribution of adherence in the Diane sample, where some people are just like, I'm not doing this. And then other people were really, really adherent, because these are highly motivated participants. But we didn't see that. And a matter of fact, it was like pretty evenly split across the adherence spectrum. So that supports our first hypothesis. And again, the reasons for this: they're 38 years old. They probably have young kids at home. They're working, and they can't just stop. If they're a school teacher, they can't just stop and take a test when we fire off a notification to them, or if they're driving or, doing these things. Whereas older adults have much different life structure. They're just as busy as the Diane people in many respects, but, they don't necessarily have the structured demands that the younger Diane people do. In reliability, we're really interested in what we call between persons reliability. And this is basically how much can we distinguish individuals compared to everybody else in a study. And that is given by this equation. And if you look on the bottom, there's a little n. And basically, if you give a really unreliable test enough times, you will get super, super high reliability. But that's not really what we want to see. We want to give the test like kind of as few times as possible. We want to sample people across occasions, but we want to be able to get a really reliable estimate if we averaged across all those tests with as few administrations as possible. And so that's the formula that we use for this. And our goal was to achieve about a 90% estimate of reliability for each measure. It's an arbitrary number that we just picked. I think this is just fascinating. In the Diane sample, first of all, this is the number of sessions. So you see 4, 7, 16, and 27. These are just numbers like based off of the average numbers of tests that people complete. Look where they start, the difference between the two. So the older adults start being very, very unreliable after 4 sessions. And then they don't asymptote until at least like 16 or 18 or even more sessions. Whereas the Diane participants start out with extraordinarily high reliability, and all of them reach our criterion by about 14 sessions of 0.9. Whereas in the older adults, they don't get there until like they complete almost all of the 28 sessions. So there's a huge difference in reliability. So yes, the Diane participants are much less adherent. They're completing way less assessments, but the reliability of the data is like even stronger than the older adults. And I think this is an age effect, which might be a proxy for a technology familiarity effect. So I think they're two separate things. I'm not totally convinced that age and technology familiarity, they're highly, highly correlated. But I think as people become more and more fluent with technology familiarity, I think this gap will shrink down. Then finally, we want to look at practice effects. This effect is massive. This is like a Cohen's d of about 1. So in the ADRC sample, first of all, you can see there's a big intercept level effect where they're performing worse than the Diane people at baseline, but there's almost no growth or almost no change over time in the Diane sample across the week. Whereas the older adults start about 0.9 standard deviation units lower, and then they end about 0.5 standard deviations lower at the end of the week. And so that's a pretty massive interaction with a really powerful signal. So there's much more practice effects going on in the older adults than the younger adults, which is the opposite of what we see in the classical literature. And then finally, we wanted to look at the correlations between our smartphone app and a composite measure and like the equivalent of a pack that we have in both our older adult sample and in the Diane sample. And sure enough, there was a stronger correlation in the Diane sample, despite completing less tests, of about 0.78, and it was about 0.58, I think, in the older adults, or 0.6 rounded up. So there's all these hypotheses ended up being true. And just, I'm going to show you one last slide. It's actually not in the paper, but interestingly, these correlations carried over into biomarkers as well. So there's just stronger correlations between the ARC, the smartphone measure, and correlations with, there's stronger correlations between the ARC smartphone measure and imaging and biomarker outcomes in the Diane sample than there were in the older adult sample. And I'm not really sure what to do with this. We didn't include it in the publication because it wasn't one of our hypotheses, but we did find this. Okay, I am done. And I'd be very happy, very interested to hear what you guys think, especially about the last study. And I want to thank a couple of people first. Andy, my former postdoc, Matt, also my former postdoc, and my two PhD students, Hannah and Samita, who actually just got her master's last week. So I need to update that to Samita MS. And also my long-term collaborators, Randy Bateman, John Morris, Eric McDade, my lab manager, Sarah, my hopefully future grad student, Ruby, and Marty Slowinski at Penn State. So thanks very much for having me. Thanks to Diane for inviting me. And this has been a really fabulous trip. Thank you.